Hello everyone again and welcome to this particular video, and in here we're going to be exploring a type of coupling that involves the formation of a new sigma bond bringing two R groups together, and this is actually done in the presence of palladium. But this type of coupling is actually called Suzuki's coupling, and Suzuki coupling is quite interesting because Suzuki actually used a type of reagent as an intermediate reagent that speeds up, I would say, the formation of our intermediate reactants, and that leads to the final formation of our product. And this particular step is actually first called the hydroboronation, and this hydroboronation step is going to be dived into in future videos in terms of different case scenarios in terms of how Suzuki coupling reactions is applied in transition metal catalysis chemistry. So in here we're going to see the mechanism, and before we actually dive into this particular mechanism, please don't forget to subscribe so as to catch up on the new videos involving the different forms of Suzuki coupling that is to come. So let's move in here to the mechanism, and usually for the mechanism, how you detect this reaction to be called a Stirling coupling reaction, not that, but instead a Suzuki reaction is that Suzuki reaction actually uses this particular alkyne, and this alkyne is actually going to be reacting in the presence of a cathodoborane, and this cathodoborane is actually the big signature reagent that actually performs the first step in the presence of heat, and then the next step is actually going to be involving a palladium complex with the aromatic halide or triphthalate, and then the two intermediate reagents would then come together to form a specific complex that then performs our final step, which takes and creates our final product, which actually is regioselective in a way where we have our hydrogen positioned in the same direction as that of our aromatic ring segments coming from the aromatic or alkyl aryl or alkyl halide. So in here, take note that for the Suzuki reaction, we actually have the coupling of our particular boron segment here, where this boron is actually going to be forming a new type of complex called a boronic acid or ester, and this actually, once created, will then be incorporated into the violin aryl halide or triphthalate complex that then leads to the formation of our product. That is the key idea behind Suzuki's coupling reaction. So let's look at the big mechanism step in here and looking at how the arrow pushing is actually facilitated to the creation of our final product. So in here we have our alkyne, and this alkyne is actually going to be reacting in the presence of our cathodoborane, and this is going to be reacting in the presence of heat by performing the first step always in Suzuki reaction, which is called the hydroboronation. We actually have the loss of our first pi bond, forming a sigma bond between the carbon and that of the boron, and then the next is the cleavage of the boron hydrogen bond to form a sigma bond between the hydrogen and that of that carbon. So therefore, in this case, we have a specific regioselectivity for the less steric hindered position. Therefore, the cis position between the boron and that of the hydrogen is actually facilitated in this particular step, and this particular complex here is called the violin boromate. So this is actually the first step you should recognize in here and keep that into account, because it will be crucial for the following step in here. So the next step here, take note here, is now we're going to start off with step 2, which involves palladium, which initially start off as oxidation number 0, and so it has to go through the oxidative addition step where we actually have a violin or aromatic halide, which in this case is the aromatic bromide, and this is actually going to be reacting with our palladium O or 0 and palladium 0, which in this case the palladium gives its electrons to the aromatic carbon, and that carbon with the bromide actually cleaves, and then the bromide actually forms a bond with the palladium. Therefore we have two bonds created, one between palladium and the aromatic carbon, and the other bond is between palladium and that of the bromide. Therefore in here we actually have the oxidation number of this complex to be palladium 2. So this actually is crucial because now we have two active groups ready for a step called the transmetallation with the alkaline bromide, and this actually is going to be done in here in the presence of a base, because this is really important because the base accelerates this transmetallation step. Therefore our base is going to then remove the boron compound segment between that and the carbon that has a sp2 hybridized state. Therefore our sp2 carbon will then form a carbon bond, carbon palladium bond with the palladium complex in here, and then we actually have a good leaving group in that palladium complex, which is the bromide. Therefore this bromide then forms a specific cluster with boron in that particular side product, which we don't care about, and we have our new complex with palladium established, where we have palladium forming a carbon bond with the alkene, but a carbon bond as well with the aromatic segment. So this actually then leads to the final step, which is a spontaneous reaction, which is actually the product formation due to the process called reductive elimination, where we regenerate our palladium 0, and sometimes it's performed in the presence of a base, but other than that it just goes in spontaneously, where our aromatic palladium carbon bond cleaves and then attacks by nucleophilically or SN2 type style, and this actually leads to the cleavage of a bond which becomes or gives back its electrons to palladium. Therefore palladium actually forms its palladium 0 or regenerates its original state, and we actually generate our final product right there, which in this case we have our R1 R2 all C's to each other, and we have our hydrogen and the aromatic segment also C's to each other in position. So in here we've generated our final product in here, which is an indication of our specific mechanism for a SUZUKI coupling. The key takeaway message here for SUZUKI coupling here is the hydroboronation step, and after that you actually perform your oxidative addition between your aromatic or your specific violin, aryl triphthalate or halide. We actually have to perform that reaction with the palladium complex, which in order for we to create our palladium 2 from palladium 0, so that that will be active, and then once that is done we can then form our transmetallation step in the presence of a base to form our intermediate reagent that brings the aromatic segment and our alkene segment together. Therefore this will lead to the formation of our final product by reductive elimination. So that is it for SUZUKI reaction initial introduction, and then the next one, in the next videos, we're going to focus on the hydroboronation of octane, and this is actually a follow-up to what we did in this particular video, or an application in here, and something you need to take note of and be aware of. Now the next one we're going to look at is how stereo control synthesis is actually leads to the formation of a EZ diene formation reagent or product. So that's it for this part, and then on our final video we're going to look at how that is applied to an aryl cross coupling, and also that of aromatic heterocyclic coupling. So that's about it for this particular video. Please don't forget to subscribe again. Thanks for following me through this. Please hit the comment down below, let me hear your thoughts. By that way I can talk to you in the comment section or in future videos. All the same, stay smart as always, and always believe in yourselves.